for your, for practice. And these are also simple things, given that you are already expert in it. So it's simple, but I don't mean that everyone, of course, everyone will not know. Some of you may do not know that what is this, right? Or what is this. So if there is no shame, there is no hesitation. You raise your voice. If you ask me, you can message me, you can email me. If you don't want to ask in person, publicly, you can just email me. I will try to explain this individually to you, no problem. But if you do not ask, and I also do not, because some of them probably I think that you know, that I will escape and then you will not know, so it is not good for you. So please, if you do not know, message me or ask a question. So can anybody tell me what is the name of this? BAS, BAS. Can anybody tell me what is the name of this BAS? BAS, BAS. Are you typing in? Barium something. Jonathan, I like this answer. Yes, this is something, of course, is a matter. Juliana, barium sulfate. Anyone wants to chip in? Barium sulfide, Taha. Barium sulfide. Michelle, barium sulfate. Okay, I have got a wide spectrum. This is good actually. This is a healthy answer, the diversity of the answer. Yes. So some of they said that barium something is of course barium something, but barium sulfate. It is not SO4 or SO3 or SO2, right? It is S, only sulfur here. So it is barium sulfide. It is only S, so it is barium sulfide. Just like hydrogen sulfide, we know, right? Yesterday, some of us were doing the, I don't know what we are doing, yeah? Mercury, no, not mercury, lead sulfide, you are decomposing, and then the smell of gas came out, the rotten things, rotten egg, that is a hydrogen sulfide, H2S. So similar to that one, the name, it is sulfide, barium sulfide, okay? So it is not sulfate. If it were SO4, it would be barium sulfate, but it is not SO4, only S, so sulfide. Some of you, I see that you did the correct answer, so it's good. Can anyone tell me what is the name of this? H2O. It should be the hardest one. Water? Water molecule. Yeah, this is what we know. That is water. But what if we say that it is a dihydrogen monoxide? Will you drink? If I say it's dihydrogen monoxide. How many of us will drink if we say it's dihydrogen monoxide? Yeah, but those who are scared of chemical, everything they say, oh, there is chemical thing, so cannot touch, cannot say. That is the problem. If you try to see the chemical, everywhere is chemical, right? Whatever drink we drink, whatever food we eat is kind of chemicals. So there is a bad thing is given on. People has given the name of chemical as everything is bad. The medicine you're taking is a chemical as well. Tea is a chemical, coffee, caffeine there. So people has tarnished the name of chemistry by this name. And I'm so sad for this, that chemistry has been battered with that type of bad side things. That is, chemical is bad thing. Everything is chemical, my bro, right? It It is not the chemical is bad. It is the bad chemical which is bad, or it is carcinogenic, or what is bad for health is bad. Anyway, it's too much. Actually, it's not the thing that we should discuss. I mean, it is not our scope of discussion, but it just came out. And so on. So if we do like this, it will take hours to finish this one. And for this purpose, I have seen magnesium oxide. So magnesium has two, right? Magnesium has two valence. So magnesium, it will be magnesium oxide in this way, because magnesium has two valence. Valence is two. Oxygen has two valence. So two magnesium plus two magnesium, two oxygen negative will come together and form a bond, which one is magnesium oxide. And hydrofluoric acid, hydrogen and fluoride, all are 1-to-1 electron exchange, and this is hydrofluoric acid. Ammonia, NH3, that we know, that is the ammonia. Carbon tetrafluoride is this one, nitrogen dioxide. And what else? Potassium iodide. Potassium iodide is here. I will make this answer available right after this class, or maybe at night, because after the class is too late and I'm too hungry and tired. Okay, so iron, what is this? What is the name for this? Can anybody tell me what is the name for FeNO23? Clarence, fancier name, okay, cause drink. Oh yeah. Whenever you drink water, remember that you are drinking a fancy chemical, right? Dihydrogen monoxide. Iron 3 nitrate. Okay, is that something? Yeah. Okay. So iron 3 nitrate, who says it? It's good actually. Thank you, Amanda. All right. Thank you. Anyone wants to try? It's okay to make mistake. Myself make mistake every day, right? Iron 3 nitrate, Jason and Amanda, thank you. Anyone wants to try? Any other thing that is coming to your mind? Yes, Tiffany, thank you. Jonathan, no, but you can try actually. There is no harm, no marks. Okay, nitrite and nitrate. NO3 would be a nitrate. NO3, and of course there will be two negative charge on it. One negative charge on it, and we will see the loose structure of this NO3 in a bit. So NO3, one negative charge will be nitrate, but when there is NO2, it is a nitrite, right? NO2 is there, so it's the nitrite ion. So it is iron 3 nitrite. Iron 3 nitrite, right? So this is the correct answer for this, and I don't have to talk about this one, right? This one, NO2, do I need to talk about it? You already know the name. What is the name for this? Is it a nitrite? Nitrogen dioxide, yes, it is nitrogen dioxide gas. So yeah, nickel carbonate as well. Nickel is coming from here, and then carbonate 3. So by this way, we can just write nickel 2 carbonate. And in this case, nickel has 2 valence to hold this carbonate. That's why 2 is used here. And it is a transition element. That's why. which group of compounds are ionic compounds and which group are covalent compound? How can you tell? Group 1 or group 2, which one is ionic and which one is covalent? Is there a cheapest or not cheapest actually? Is there a easiest formula that you can find or think that we can find out faster? So for this group 1, you see the difference between the group 1 and group 2 is here one element is metal, another is non-metal, right? Potassium, magnesium, barium, then iron, nickel, all are metal. But oxygen, nitrate, carbonate, all are non-metal here. But for this case, group 2, hydrogen and oxygen, hydrogen, fluorine, nitrogen, hydrogen, carbon fluoride. So all these are non-metal. So when there is a bonding between non-metal and metal, we know from that criteria that when there is a bonding between them, metal, non-metal, there is more chances that it will go towards ionic bonding. And when there is non-metal to non-metal, it is mostly covalent bonding. Okay, so this is how we can find, or we can roughly estimate that group 1 will be more ionic charge, bonding between them. To know exactly the whether it's ionic or polar covalent, we have to find out the electronegativity between them. Okay, so this is ionic bonding. We have seen already when there is a electronegativity difference between them is more than 1.9 in fact. So there will be a ionic bonding between them, and it is based on the electrostatic energy when these two elements are nucleus coming together, they are forcing together, there will be a electrostatic bonding between them, and that electrostatic bonding is governed by this, or can be calculated, can be estimated by using this equation, Coulomb's law. And we have seen this before actually. All right, so this is Coulomb's law, and this is if that the r squared is too big, or they are far apart, or r squared is too big, then the attraction energy, electrostatic energy will be reduced, right? And when they are reduced, there will be no bonding between them. Or if the charge is very big, or Q1 or Q2 are very big, K is a constant anyway, Planck's constant, so that does not change. But Q and QQ means charge. If the charge grows, it is proportional, right? The F, that is, it should be E actually. All right. So this E, electrostatic energy, is, or force, then it should be F, okay. So E is proportional to this Q1, Q plus and Q minus, that means the charge, the separate charges that is involved. And it is inversely proportional to this R squared, or the distance. So when the Q and Q increases, the charge or the attraction will increase as well. Now, given on this factor, or this estimation, equation or information, number 2 it says that given the distance between sodium +1 and chloride is -1, Q1 and Q2, is 0.276 nanometer. Estimate the bond energy of sodium chloride in joule per ion pair. Then convert the value to kilojoule per mole. Hold on, I need to open PDF so that I can write. Okay, so I can write on here, and it says that E, that I mean, we have to find out the E. So to find out E, if we use the same equation, can you see? Can somebody confirm me if anybody can see what I'm trying to write? Hello, can you? Yeah, okay. So E is the electrostatic energy between them, sodium and chloride. When sodium and chloride are coming together, right? Sodium it is, and this is chloride should be a bit bigger anyway. So this is coming together, and the difference or the force, attraction force between them, if it is y-axis, this is x-axis, is the potential energy. We have seen this before. I will see it later, and this is the distance. Okay, the potential energy, PE. Oh my God, so, and this is the distance. So what will be the E for the sodium and chloride? If we do this calculation, and by this calculation, just put the values here, the same thing, only Q1 and Q2 is positive 1, positive 2, negative 2, negative 1, sorry, and then the D will be 0. Here is given, right? The 0.276 nanometer, so 0.276 nanometer here. The good thing is this is nanometer, here it will be nanometer as well. If it were a micrometer or any other thing, then you had to adjust it accordingly to do this unit conversion. Or anyway, you had to convert it to become the same unit. Otherwise, we cannot multiply or add or subtract from the same thing. So this will be the thing, and okay, so the E, estimate the bond energy. So this one that will give us the bond energy of sodium chloride in joule per ion, in joule. But for ion pair, we have to find out, this is the joule per ion, right? This is the joule per ion pair. This is the joule per ion pair. So this is joule per ion pair. Right. So now we have to find out that how many ion pairs in 1 mole, because it says that kilojoule, it is joule, and it says kilojoule to, after we find out, already this is good, and at this position we can find out the joule per ion pair. But the question is, another thing is kilojoule per ion pair. So since we have found the joule per ion pair, now just convert it to joule per mole. And again, in 1 mole, how many ion pairs will be there? Anybody? In 1 mole, how many ion pair should be there? I'm looking at your chat box now. Avogadro's number of ions, right? In 1 mole, Avogadro's number of ions will be there. So whatever, let's say we got the result from here is X. So X should be this is O. X is a bad choice then. So what should I say? Got the Y, the result from here Y. So Y should be multiplied with the ion, Avogadro's number 6.023 times 10^23, 10 power 23rd. Okay, iron. What is that? It will be ion pair per joule, per mole. Ion pairs per mole. In 1 mole, there will be always Avogadro's number of particles, human, mobile phone, data, whatever. 1 mole is equal to Avogadro's number, whatever it is. Okay, so and then it will give us per mole, but to convert it to kilojoule, right? From here it was joule. It was joule here. Y was in joule. It was in joule. So convert it, we have to divide by 1000 joule. 1000 joule was kilojoule, right? So now we have to divide by 1000. So that it will be, or you can divide first by 1000 and then multiply with the Avogadro's number. No problem, the same thing. So it will be kilojoule per mole in this case. So in this way, we will find that it will be minus 504 minus 504 kilojoule per mole. Okay. So another part of the question is saying, do you expect sodium bromide to have a higher bond energy than sodium chloride? Do you expect sodium bromide to have a higher bond energy? Higher bond energy means, do you think that the sodium bromide is higher, or is stronger? What I want to hear from you as well, do you think it is higher or lower?
I think it's lower.
Okay, I got one answer. Thank you. Anyone else want to chip in, participate? It's not about participating, it's just what you think. Okay, Clarence, lower. So we got 2 answer. But why it is lower? Why, when it is lower, you say why it is lower, why it should be lower? What is your answer for that? Chlorine more reactive than bromine. One answer. Jason, ionic bonding is stronger. Ionic bond is stronger in what, Jason? Your answer does not carry the full thing that you are trying to say. So we do not know what your difference in distance, D. Yes, we have the difference in distance. As we go down the periodic table, if you have the periodic table, I cannot switch between I can see on my computer, but I cannot see switch between the screens. But if you can see, or let me show you actually, maybe once I can go, not all the time. Periodic table. As we go down the periodic table, this is the halogen, right? The halogen, and then fluorine, chlorine, bromine, iodine, astatine. So all this, as we go down, we know that it increases, right? The size increases. Fluorine is very small and compact. Chlorine bigger than fluorine. Bromine is even bigger than chlorine, and iodine, of course, is much bigger. So in this case, when we go down the periodic table, the size is expanding, getting bigger. That means when these two, fluorine and chlorine, for this question, what is the question here? This sodium and chloride, right? Sodium and bromide. The question is asking whether sodium and bromide will have a stronger bond or weaker bond. Now, sodium is the same thing. It is binding with the chlorine, and sodium is binding with bromine as well. bromine is increasing the size. So when the size increases between bromine and sodium, the bond becomes weaker, right? With the chlorine, it is much stronger because it's staying together. The R is less. For sodium and chloride, the R that is we're dividing by R, that is less. But for bromine, it is increasing, and in that case, since it is increasing, so the bond energy will be lower for sodium bromide. And since it is lower bond energy between them, it will be much more reactive than sodium chloride. And sodium iodide is even more reactive for the same thing. So as we go down, iodine, for this case, we will see it in a bit. So in this case, in this way, when the bond energy is weaker, the energy is weaker, then it will be more reactive. Okay. Okay, so typical physical properties of ionic bonds are high melting points, soluble in solubility, water increases. The ionic bonds are usually higher in melting point, okay, because of their bond energy is much stronger because of the electron. I mean, you know how they form, right? And solubility of water also increases when the electron is transferred rather than shared. They have the electronic, there is the tension between by sharing the electrons, and polarization. There is a polarization. So water is a polar solvent, and it follows the chemical motto that like dissolves like, right? So since it is a polar molecule, the polar molecule will be dissolved in the polar solvent, and that is why the ionic compounds get dissolved in water. They are not a good conductor when they are solid state. When they're solid state, the electrons are, I mean, they are mostly, they will have a crystal formation, and that is why the electrons are not very available when they are solid state. So they do not conduct the electricity, but when they are in liquid state, they will conduct the electricity, or in molten state. Okay. Now there's here, that is the I was talking about. That sodium fluoride, we see that it has a bond energy or distance, sorry, bond distance is 231 picometer. 231 picometer. I forgot exactly how many picometers 1 meter, but picometer is very small. And as we go down, we see the sodium iodide, the distance increases to very high. Calcium oxide is from different group, different period, but we will talk a bit with it soon. And now we see that the lattice energy is how, I mean, the amount of energy is needed to separate molecules or atoms from, sorry, not molecules, atoms from one molecule. Okay, you are breaking it. That is the lattice energy. You are breaking the atoms from a molecule. It is lattice energy. How much energy does it need to break apart one molecule, divided into its number of elements? Okay, and because of this, you see the melting point is very high because of their lattice energy is higher and their distance is low. So the melting point is higher, right, for sodium fluoride. As we go down, with the melting point start to reduce. We are not talking about the calcium oxide, we'll talk a bit. So as we go down, it starts to decrease. And when it decreases, it means that it is easy to break. It easy to break apart their lattices. It not necessarily breaking the bond of the molecule, but it is not at the perfect place to have the strongest how do I okay it is not breaking the total bond like sodium and chloride. You are not breaking it to sodium and chloride, two different atoms, right? It is not like that. But sodium chloride, they are together. When the lattice energy is, the lattice energy, you are breaking that. That means sodium chloride they are still sodium and chloride, but not that tightly bonded together. Okay, so that is called the lattice energy. And melting point is that the thing that it is opening up, it is releasing. Yeah, they are not staying together, but still they are maintaining the relation. So that is the melting point. So as we go down, you see the melting point is reducing. But the question now, why the sodium fluoride, it falls between the calcium oxide, sorry, sodium and fluoride and sodium chloride, but it has the higher melting point than these two, right? Why does it have a higher melting point than these two? What is the thing that is going on here? What is the things going on in here? Compound the lattice energy, I already have discussed. Question C says outline the general relation between lattice energy and melting point. I have discussed. Explain why. Okay, number D, I'm at number D now. Calcium oxide has much melting higher temperature. It means much means higher temperature than sodium fluoride or sodium chloride. Because here calcium ion is 2+, right? It releases 2 electron to become 2+, and oxide, it takes 2 electron to become 2 negative, oxide ion. So since the charges are higher, the electrostatic force will be much higher than their than sodium chloride or sodium fluoride, because they are sharing only one. And if there is one, if we know that, if we remember this equation, it was equal to K is a constant, Q1 and Q2 over R squared. So when it is 1 times 1, or if it is 2 times 2, 2 times 2, when is 1, so it's exponentially increasing. The distance is not that different from the sodium chloride, but this Q1, Q2 multiplication is increasing exponentially, and that is why they have a much stronger lattice energy needed. Much stronger lattice energy they have. And that is why it's hard to break. The graph above shows the question number 4. We are moving to covalent bond, and it says that the distance between how does the covalent bond forms? By sharing the electron, right? But none in the world is so much selflessly shares anything, right? Who does? Anybody knows? It's the social media. So do you see anybody's sharing anything selflessly with pure interest of anything? Same goes for the chemicals as well. They do not share anything out of 100% what do you call it, selfless motive. So there is no pure covalent bond. Okay, there is no pure covalent bond. But when these two nucleus coming together, they are having, by sharing the electrons, they are having the minimal potential energy. So they form this there is the I mean, at a certain distance, they will fall between them and then they will form the bond. So we already have, this says that circle it. So we have already circled it here. And it says, question number B, that according to the graph, what is the approximate average bond length for the system of atoms? How can you tell? What is the bond length for this atom? Here we see it is around 7 or 8 nanometer. Let's say 7 nanometer. So bond length maybe 7. If somebody says 6, should be okay. We are human, so we can make this type of parallax error. Okay, so this is a bond length of this. Okay, and question number C says that if the atoms in the graph were at the most stable bond length, how much energy would be needed? All right, is how much energy would it need to separate 1 mole of atom pair completely, or released to form 1 mole of bonded atom pair? Anybody wants to try? How much energy, looking at this graph or figure, how much energy would it need to form a bond between them? Whatever 2 atoms, it doesn't say what atoms are these, but 2 atoms, right? Any 2 atoms, let's say A and B, mixing together. Anybody wants to try? It will be 200 kilojoule per mole, right? If this amount of energy is given, we give this energy to this, given means what? If we heat it up and give this 200 kilojoule per mole of that molecule, then it will get that energy and release this energy. Okay, or if they have to bind together, A and B, let's say A and B come close and make this bonding at this position, they have to release this 200 kilojoule of heat so that they can be together. So this is, in both cases, it will be 200 kilojoule. What happens if it is more than 15 meters apart, and what happens when 5 meters apart? When it's more than 15 meters apart, this is 15. Let's say it's 15 here. So when there's 15 meters apart, A and B stay there as independent or molecules there, or atoms. They do not react, or they do not make any bonding. But if it is less than 5 nanometer distance, that is this one, right, their repulsion energy is too big, is even more than when they are staying single, staying alone, is more than, so they will repel each other. They will go away very far. So there will be no bonding between them in that case. The following is a table comparing the average bond length and average bond energy of 3 halogens: chlorine, bromine, iodine. And average bond energy for bond length for chlorine and bromine and iodine, you can see that 199, 200, 228, and 268. And the average bond energy is, of course, when there is smaller, so bond energy is higher. Explain why the average bond length vary for the 3 halogens shown in the table. Of course, because of their size of the atoms. They have different bigger size. Chlorine is smaller, bromine is bigger than that, iodine is bigger than that. So that's why iodine will have a bigger size or the bond length between them, and that is why the bond energy is less between them. How does the bond length affect the strength of the bond formed? This one is because we can see it clearly that as we go up, the bond energy is increasing, and that is why chlorine will have much higher bonding, stronger bonding, and then it will be the less reactive than iodine or bromine. Iodine will be the most reactive because it has a longer bond and less bond energy to break. So it will break easily between them. It will break easily and react. But chlorine will take time and heat to break this, not as easy as iodine. So the most chemically reactive halogen is iodine. It should be that we just have seen. And most thermally stable halogen. Any guess on this? Thermally stable halogen. Which one is the most thermally stable halogen? Guys, are you with me? Listening? Thermally most stable halogen should be chlorine, right? Somebody answer. Yes. So it will be chlorine because the thermal stability refers to the stability of decomposition. It will be hard to decompose chlorine because it has a higher, it takes more energy to be decomposed, and the boiling point and melting point of chlorine has okay, chlorine has lower BP and boiling point and melting point because compared to the halogen. This is because a non-polar molecule and experience the weaker van der Waals, the force between them. Why is non-polar? Because chlorine, both are the same, electronegativity is same, right? When this is chlorine, both are chlorine, so the electronegativity is same between them, and then the difference between electronegativity is 0. So that in this case, it is purely covalent bonding. There is no electron density to any particular chlorine, right? So it is a pure covalent bonding. Okay, some answer actually. But do you see that I am saying what I just said, the opposite thing of what I am saying just now? I said there is no pure covalent bonding. Yes, that is true. But only the difference in electronegativity, the value of the electronegativity is difference is 0 for the chlorine. That is why it has a less electronegativity, a 0 electronegativity. That's why it should be, we should consider is very what do you call it, covalent bonding. Sorry, yeah. Just 1 second. Okay, so I was telling that there is no chlorine, covalent bonding, right? But the difference is only the electronegativity. The value of the electronegativity is the difference, and then this value is telling us that it should be a pure covalent. But when we look at this structure, or we try to see it in an atomic level, what happens is chlorine is electronegative. First, they want both this chlorine atom and this chlorine atom. There is no difference. Both are the same thing. So they have very much electronegativity. So what will happen is, although they are coming together and forming this chlorine 2, each of them are trying to draw the electron towards it. So what will happen is the electron will go towards this chlorine one moment, to that chlorine another moment. Okay, and then this chlorine will again snatch the electron here. So it is going. So at a certain moment, this chlorine is having more electron than this one, and another moment this chlorine is having more electron than this. So in this way, but they are balancing it. One moment is there, another moment is there. So this is, and that is why they would call it, we see they behave like a covalent bonding. What I was telling is why I was telling this. The most chemical reactive halogen, iodine, yeah, because of this, because the iodine will break out faster. And chlorine, thermally more stable halogen. Oh, I was telling this because I was telling that they will, the melting point and it's not the same temperature that they will not try to, it is hard to melt them away because with the high temperature, because of this. Yeah, no, I know what I was saying. So because of this, the melting point of chlorine has a lowest boiling point and melting point compared to other halogen, because they have a low non-polar character. The bond is a non-polar character, and they experience the weakest van der Waals force between two molecules. So when there is a chlorine here, another chlorine is here, another chlorine is here. So between them, they will have very less van der Waals bonding. Van der Waals force is kind of attractive force between more polarized electronegative, more positively charged and negatively charged ions or molecules. For example, when water is there, we draw water in this way, oxygen and hydrogen, right? This is oxygen, this is hydrogen, and this is hydrogen as well. So for another oxygen, it will have hydrogen here and hydrogen there. So between oxygen are very much electronegative. We know that this is partially negatively charged. Hydrogen is very partially positively charged. Okay, positive. So between them, there will be an attraction force. And for this attraction force, there will be a attraction that is called van der Waals attraction, and that is why water has higher boiling temperature than any others similar molecules. So same thing goes, and chlorine, they do not have, they are very much behave like a non-polar bond, so there is no attraction force between them. Okay, so electronegativity and bond polarity. Now, hydrogen fluoride, what type of bond do you think they will have? If we look at this table, hydrogen has 2.1 and fluorine has 4, the maximum the number for electronegativity. So between them, the difference is 1.9, and due to this bonding, I mean 1.9, it is not more than 1.9, or it should be more than 1.9 so that it could be an ionic bonding. But since it is not, it is very much polar. What do you call it? It's very much polar bonding, right? It is very much polar bond. And another thing is the electronegativity difference. Electronegativity difference, if it is more or equal to 1.9, sorry, it is, if it is more or equal to 1.9, then it will be ionic bonding. So it will be ionic bonding as well. It is ionic bonding as well because it is more or equal to 1.9. And hydrogen and fluorine both are non-metal. We discussed it before that when there is a metal and non-metal bonding together, they will form ionic bonding mostly, right? We know that mostly when metal and non-metal forms the bond, they form the ionic bonding. But in this case, you see, it is hydrogen and fluorine, and they both of them are non-metal, but still they are forming ionic bonding. Sodium trichloride. If sodium trichloride, if we see that the bonding between, I mean, electronegativity difference, here we see the sodium is 0.9, right? And, oh, it's not sodium, it's nitrogen. Sorry, it's nitrogen, yeah? It's nitrogen trichloride. So chlorine and nitrogen, here it is nitrogen, here it is chlorine. Both of them has the difference, I mean, value of electronegativity is 3. It's not exactly 3, but to round off, it will be 3. And then electronegativity difference is 0. So if electronegativity difference is 0, it's supposed to be non-polar covalent bonding. Okay, it is not, it is, I mean, when we define the bond, we should say it is a covalent, pure covalent bonding, right? Pure covalent bonding. I'm not writing it whole, but you know. But the problem is nitrogen is smaller than chlorine because nitrogen is here and chlorine is there, the next period and next group, next group. So chlorine is much bigger than nitrogen. Nitrogen is smaller. When it is smaller, it is compact. It is has more electron affinity, so that it will be always here is the nitrogen, here is chlorine. So it will attract more towards themselves, nitrogen, and that is why it will be always the electron density is bigger than here. Although it is bigger, electron density is bigger on this side, and because of this, the bond between them is not very, I mean, still it has the difference between them. Electron effect, they should experience an electron effect between them. Aluminium trichloride. Now we go for aluminium trichloride, and the electronegativity difference is 1.5. If we go to the table and see, it's 1.5. And since it's 1.5, we know from this rule that it's more than 5 and less than 1.9. It will be polar covalent bond. And aluminum is metal, chlorine is non-metal, but they are supposed to, aluminum is metal, non-metal, between them are supposed to be a ionic bonding, but still they are forming a covalent, pure covalent bond, not pure, sorry, polar covalent bond because of their electron density. So it will be very much polar, but covalent bond nonetheless. Any questions so far? Hydrogen bond. Yes. Yeah, in water, they form the hydrogen bonding. Any other question anyone has? Okay, so question number 8, it says, when can we go to this? There are some funny questions there, we will see in a bit. So question number 8, it says that difference in electronegativity and type the bond, we have to find out what are the difference. Of course, you see, okay. Okay, hydrogen bond, there is the electronegativity is different. So of course, non-polar covalent bonding. HCl, it is 0.9, the difference. So it will be polar covalent bond. Sodium chloride, the difference is more than 2 or more than 1.9. So it is ionic bonding, carbon and hydrogen. It is a non-polar covalent bonding. Forming because of the electronegativity difference between them. We just simply calculate, subtract the electronegativity difference from the chart in the table. So now we see that instant coffee, compare the following. Question number 10 says that complete the following table, predict the polarity of compound, polar or non-polar, and type of bonding, ionic, polar, compound, and or polar covalent bonding based on the solubility in 2 different solvents, water or turpentine. Turpentine is a solvent, and it is a non-polar solvent. It's organic solvent, non-polar solvent. So instant coffee, it dissolves in water. Okay, so what do you think? Do you think this is a non-polar or polar? It has a polar bonding or non-polar bonding? Since it dissolves in water, and we know that, yes, thank you, Clarence. So since it dissolves in water, and then we know that like dissolves like, so that water is polar, it will only dissolve the polar thing, non-polar. You will not be able to dissolve oil in water, can you? Have you seen the water and you put one drop of oil in the water and it floats, right, on the surface of the water? Some oil can, if it is a petroleum oil, it will sink, but mostly it floats. So it doesn't mix. That is because water is polar, they are non-polar. Peanut butter. So peanut butter is soluble in turpentine, so that it is the non-polar. Its polarity is less, non-polar, and it will be non-polar covalent bonding. Sunblock lotion. Don't put this turpentine, you know that it will be a non-polar, because if it is polar and you put it on your body and go in, jump in the sea, after few seconds is dissolved, because the water will dissolve it if it is a polar. So it cannot be a polar one. Food coloring, however, cannot be a mostly cannot be non-polar, because when we prepare the food, we have to dissolve it in water and then mix it well nicely. If it does not get dissolved in water, so we cannot use it. Or other way, it has to be dissolved in oil for some applications, some food coloring, to be used in cakes, I don't know, maybe something like that. So that one will be non-polar, but for this case, it dissolves in water. Candle wax, iodine dissolves in turpentine, and from there we know that if we do not even say that iodine and you do not give the turpentine, you also know that it is a non-polar, because both of iodine, they have the difference of electronegativity is 0. And that is why they are non-polar. Okay, so sodium chloride, what will be the bonding type, polarity, and suitable solvent? Do you want to participate, please, so that it will be, after that, we will go for a Menti question. First of all, sodium chloride, okay, should be in one page. Should be page, okay. So what type of solute sodium chloride will be, and the bonding type, polarity, and suitable solvent should be needed. Ionic polar water. Wow, good. Thank you. Many of us are actually participating. I am so happy to see. But I just want to, Alvin, you there? It will be a name present actually. Taking the yeah. So
Yes, sir. Yeah.
okay, okay.
I'm still
So
eating.
what is? All right, it's okay, no problem.
Sorry.
Easy. What is your opinion for the sodium chloride? What do you think the bond type is? What do you think the polarity about it? Any idea?
It's polar.
Okay. And suitable the solvent for sodium chloride? Is it oil?
Water.
Water. All right, good. Thank you. So now may I, where is it? Who are they here? Precious, are you there? Precious. No. Anupaja, are you here? Hello, Anupaja. Anupaja, you are not here. Okay. James. James Fa, are you here? Precious not here, James Fa not here, Anupaja not here. Jolene? Jolene. James, my mic is not working. Okay. Okay. Yeah, open your mic. Jolene, James' mic is not working, but I hope by next class his mic will be okay so that we can talk. But Jolene, what is your opinion for the second one? Not second one, isopropyl alcohol. For isopropyl alcohol, what is your opinion? Hello, Jolene, open your mic and talk. What do you think that suitable solvent for isopropyl alcohol will be? Jolene, are you listening to me?
I'm not sure.
Okay, no problem, but at least I made you talk. That is a good thing. Okay, so anybody wants to try?
Water or ethanol?
Alvin, thank you. Water or ethanol? Anybody agree with that? Clarence, covalent nonpolar oil? Actually, all oil are nonpolar, so you don't have to mention the oil is nonpolar, right? But yeah, it's very specific, good thing. Water, Momataha, covalent polar bond water. Yes, good. So this is the bonding type. It is isopropyl alcohol. It says that even though it looks like that it is carbon and hydrogen, but there is a hydrogen and oxygen bonding, yeah, OH bonding between them. And OH, when there is a OH bonding, it always try to polarize the thing, polarize the bonding. Right, even though it is not a polar bond, ionic bonding, of course, but it will try to polarize the bond. That means it will, oxygen is electronegative, so it will always try to take the oxygen towards it. And when it takes the oxygen towards it, the other element or other atom becomes a less oxygen or deprived of oxygen. When there is a deprived oxygen, they becomes more polarized. So this one has a heavy, this bulky one is become bulky, taking all oxygen, and this one becomes shrink. So because of this, they become polarized. And that is why isopropyl alcohol will be polar covalent bonds, and the polarity, it will be a polar molecule. All right, it will be a polar molecule. So it is P polar, PO polar, and suitable solvent, since it's polar, isopropyl water is the best and cheapest solvent for isopropyl alcohol. Something goes for our hand rub, right? Nowadays we are using a lot of hand sanitizer. Most of it is isopropyl alcohol. All right, most of it is isopropyl alcohol, and it is quite flammable. It's very flammable, so be careful when you're using it. Don't try to set it fire. Okay, baking soda. Baking soda, sodium hydrogen carbonate. All right, so when there is a sodium and carbonate there, so if we try to find out the difference between the electronegativity, we will see this ionic bonding they are forming. Okay, sodium and oxygen, they are forming ionic bonding between them. And because of that, of course, it is polar, and water will be the good solution. Sulfur powder. Sulfur powder is itself, there are 8 sulfur atoms in one bond, but all are sulfur. All right, all are sulfur. Whatever, doesn't matter how many sulfur is there, but all are sulfur. All 8 of them are sulfur. So when there is sulfur and sulfur all together, the difference between them is 0. The electronegativity, electronegativity difference is 0. So this is, of course, it's a non-polar, and since it's non-polar, so far we only know that turpentine is a non-polar solvent, so we can say turpentine will be a good one to dissolve. All right. Okay, so before we move on to our loose structure, let's try some Menti question. Can you please go to the Menti question? Oil as solvent. Yep, Ken. Okay, so go to the Menti question and then use this as a code. Use this as a code and answer your question. Which one is true, you think? Okay. Which one you think, I mean, is true, you think? And by this way, I go and make my tea and I will come back. Let me share the Menti question to you as well. Right? You need to count on and then send your, I mean, just click which one you think is the main correct answer. And later I will talk about this amoxicillin and ambroxol. What are those things? All right, it's very interesting thing. Oh, I forgot to put the question. I put the answer, but I forgot to put the question. Now you can see the question, hopefully. And please go in again. The code is changed. So I'm sharing the code with you now. Does it change? No, the same code. Use the same code. And now you see the question is saying that which one has the more polar bonds among them, amoxicillin or ambroxol? Which one has the most polar bonds? Please cast your vote or answer. Later we'll discuss what are these two things. You haven't voted yet? Nobody? Okay. I see, but I cannot see the. How do I see the answer? I see the 16 of you have voted, but how do I get the answer? Okay, the result is shows. Oh my goodness. Result shows that 9 of us choose amoxicillin, and it is quite good actually. The thing is, 9 of us choose amoxicillin. Let me show you the slide. 9 of us choose amoxicillin, 7 ambroxol. Amoxicillin is the correct answer, in fact. But why it is correct answer? Let's go and check. What is the why it is correct? We're saying, okay, so this is amoxicillin, and you see how many hydrogen and oxygen. This is carbon and oxygen, nitrogen and hydrogen. All right. So carbon and oxygen, carbon, hydrogen, hydroxyl. So 1, 2, 3, nitrogen, 4, 5, 6, 7, 8. Here is more polar bond than here. Here is carbon and hydrogen. Here is one. I cannot draw. Here is another one. Here is another one. So 1, 2, 3, 4, 5. For ambroxol is 5. For amoxicillin it is 8. More polar bonds in amoxicillin. By looking at it, actually, we can find out that. But do you know what is amoxicillin? Have you heard about it before? Anyone? This is an antibiotic, all right? This is an antibiotic, and this is ambroxol. I'm sure everybody of us has taken at least once in our lifetime. This is what is in the cough syrup. If we get cough, then this is an expectorant. It says to take the cough out of our lung. Okay, so this is called because of this expectorant. And because, I mean, why do they use, what is the purpose? Sometimes you will see that some of the medicine, mostly this antibiotic, they are having one HCl with it, right? Or hydrogen chloride with it, just to make the bond or molecule more polar. When they are polar, it helps to dissolve in water first, and also it reduces the electrons. When there is oxygen is here, if you can see on my cursor, when way to there's no way to make this thing. Okay, so if you can see that hydroxyl here, it is drawing the electron towards it from this structure. What is that structure? We have seen already. This is the benzene or phenyl structure. Is drawing the electron towards it. When it is drawing the electrons towards it, it is losing its capability. This structure, phenyl structure, is losing its capability to go for further reaction. Okay, it is losing its ability, and by this way, this type of amoxicillin or this type of antibiotic we can keep in our body for longer time. That means it becomes a slow release. It 12 hours, right? Sometimes we say that this antibiotic we cannot take before 12 hours. Some say it's about every 8 hours we have to take, not before that. So that is how it is staying in our body for 12 hours, 8 hours in that way. So it depends on how, this is one of the factors that it can stay longer. Okay, so there are two things. These are two things, and also this and halogens, especially this bromine, chlorine. Fluorine is very difficult, so we are not talking about the fluorine, but bromine and chlorine. Most of these two things you will see in the medicine in our uses. If you look, if you go to the, if you take any medicine, of course you should try to search for its structure. Okay, it is very interesting. So if you look at this type of elements that we have on in the medicine, mostly the the halogens are there, because halogens are very electronegative, more than others, and that is why they will try to attract the electrons. And because of their electronegativity, when they meet the bacteria, or not bacteria, how do you say this, microbes, yeah, when they meet the microbes, what will happen is they will try to react with the microbe cell. Okay, they will try to react with the microbe cell, and by this way they will destroy the microbe cell, and thus the microbe will be destroyed. So that is why in every antibiotic, mostly there will be this type of halogens. But halogens are very hard to put inside the ring because of their properties, their chemical properties. They are very hard to put into, and there are so many researchers going on how to put them effectively, efficiently, and easily in that, so that it becomes more easy. Anyway, there's so much, a lot of talking we'll do. Now let's go back to this, our tutorial again, and we were here. Now we go to the Lewis structure. For these two cases, three actually, no, many actually. For this Lewis structure, it says that barium dihydride. Okay, so barium dihydride, it has we have seen already that it only fills up 6 electrons, right? Sextet, it is sextet, it does not fill octet, so it only fills sextet. And for this case, boron will be sextet, but for this case, beryllium has only 4 electrons. It needs to cover it, I mean, for fill up its outer shell. So there will be 4 electrons. So it is deficient, electron deficient. These are, some of them are exceptional, so we have to remember those exceptional things as well. And for nitric oxide, okay, nitric oxide, because of its character and number of electrons, okay, first of all, what we will do is we try to find out for nitric oxide, for example, NO. We try to find out, of course we will find, not try to, we must find out the number of valence shell electron, total valence electron, okay, total valence electron. And for nitrogen there are 5 valence electron, for oxygen there are 6, so it will be 11 electron. Now what we have to do is nitrogen and oxygen, there is no center atom because there is only 2, so it can side by side, and we form a bond between them and try to fill up the octet for all of them. 2, 4, and here 6. So oxygen becomes filled up with octet. For nitrogen though, we have to have 11 electrons, right? We have to have 11. So 8 is already taken here. Now 10 and another one is 11. Okay, so for this case, this is the possible structure for nitric oxide. NO, gas, of course, because we have 11 electron. Now we count on 2, 4, 6, and 2 in here, that is 8, 9, 10, 11. So this is good. What is the difference between this one and this one? What is the difference between this? Well, the difference is the formal charge, right? The formal charge. We have to find out the formal charge, and there are some rule for formal charge. FC is F dot C is the formal charge. So the rule for formal charge, how do you count the formal charge? The valence shell electron minus the lone paired electron, LPE, lone paired electron that is still there, minus half of the bonding electron. Half of the bonding electron now they are having. So formal charge for nitric oxide is valence shell electrons are how many? For nitrogen, for this case, let's say this is our structure A, this is our structure B, right? So formal charge for structure A, nitrogen originally has 5 valence shell electron because it is 5A, group 5A, and there are 5 outer shell electron. Minus how many lone pair electrons are there? 1, 2, 3. Lone pair doesn't mean that only pairs. How many electrons are still there? So 1, 2, 3 electrons are here. Okay, and then half of the bonding electron. How many bonds it has formed? Nitrogen to oxygen, only one bond. So half of the bond, one bond means bonding electron means how many electrons in that bond, right? So in one bond there are 2 electrons. Half of these 2, let me write it, and bonding electron is 2 electrons. 2 electrons are there. So half of 2 is 1, of course. So in this case, it will be 5 minus 3 minus 1 is positive 1 charge. Same thing, if we do on oxygen, we will see that 6 valence electron minus there are still 6. 1, 2, 3, 4, 5, 6. And with this 6 and this 2, 8, oxygen already has filled up its octet, even though nitrogen did not, but oxygen already has filled up octet. All right. So this is one possibility. So 6 minus lone pair electron is 6 there as well, minus the same thing, half of the bonding electrons. Bonding electrons is 2. All right. So 2, 2, 1. So it will be negative 1 charge. So nitrogen is positively charged. Formal charge is positive 1. Oxygen is negative 1. Now we come here for nitrogen and oxygen when there is a 2 double bond between them. Well, how do we put the double bond between them? Because oxygen has a lot of electrons here, and nitrogen in this case it has, let me draw it once again, nitrogen and oxygen. Okay, there are 6. Okay, this is nitrogen has 3, 1 double bond, 1 pair, 1 lone pair, and oxygen has 2, 4, 6. Right. Altogether, if we count on, it will be 11 electrons. But the thing is, oxygen although has 8 electrons already, for this case, nitrogen has not 8 electrons, has a 2. In this case, this is shared 2 electrons, 2, 2, 4, and 5. So nitrogen has 5. Is far away from filling up the 8 octet. Far away, 5 minus 3 electrons, it's needed more. So what it will do, oxygen will do, oxygen is very generous. So it will just donate its 2 electrons towards nitrogen to form another bond. And by this way, there will be one bonding. Okay, there will be one bonding, extra bonding, and these two bonds will be moved. Let's say no. Okay, these two bonds moved to form one bonding, right? One bonding, excess bonding, and there is another. Of course, there's two bonding. So by this is how they form a double bond, and by this way nitrogen is much closer to the octet, even though it doesn't fill up the octet. 2 4 6 2 2 4 6 7. So nitrogen has 7 electrons, oxygen or still has 8. 2 to 4 to 6 to 8, right? Two double bonds means 4 electrons and it has 4, so 8. But by this way, it's 7 is much closer to 8 than 5. Okay, so this is possibility, but this is also possibility, and this is how if we see the formal charge on nitrogen is 5 minus 3 electrons unused electron here, by minus half of the bonding electron. Bonding electron is 1 2 3 4, so times 4, right? And it is 2. So by this way we see it is 0. 5 minus 5 is 0, and oxygen also it will be 0 by this same way. So this is much easy, much stable than this one. It is having, although it is good that oxygen is having negative charge, nitrogen is a positive charge, but this one they do not have any formal charge, and this is much stable, much more stable than others. For xenon tetrafluoride, xenon has the expansion of octet, because xenon, although it's a noble gas, but it, as we go down the periodic table, it expands, right? The size of the atom increases, and d orbital also introduced to that atom, and because of this d orbital they can expand their octet. So xenon as well can expand their octet, and when they form xenon tetrafluoride, fluorine is electronegative and it will not share anything. It will just fill up its octet. It's so electronegative. It's the most electronegative, and it can only form one bond. It is very important. Okay, never form two bonds for fluorine. If you form two bonds for fluorine, straight 0 mark. There will be no other consideration. Fluorine cannot have more than one bond. Okay, all right. So fluorine, when there are 4 fluorine are coming together, the xenon can bond with all this fluorine, and still it has 4 excess electron to house, to hold, and that is how the octet is expanding for xenon. So altogether it will be 2, 4, 6, 8, 10, and 12, right? So for xenon tetrafluoride, what should I write? For xenon tetrafluoride, let me clean up some part so that I can write. So xenon tetrafluoride, we have to, this is why the total valence electron, counting the total valence electron is very important. Okay, the total electrons, how much is the total electrons? Sorry, total electrons, total valence electron is important to count. For xenon tetrafluoride, XeF4, right? XeF4, there is no charge on it. XeF4. So xenon tetrafluoride, how many Xe actually? Xenon from periodic table 18, and it is period 5. So what is the total number of electrons it has? Let me check. 8 electrons at the outer shell. 8 electrons at the outer shell. All right. 8 on the outer shell and plus 4 times 7. Okay, so 4 times 7 is 28 plus 8, and then is 36 electrons. 36 electrons. All right. So now if you just make this like xenon and then put 4 fluoride at the 4 corner, right? 4 corner, and then make this fluorine octet filled up so that it is looks good, because xenon also in this way will have 4 bonds, that means 8 electrons, but this is not the case. That's why you should always count the total electron. You have to fill up, I mean, make sure that there are 36 electron as well on this element or ions or molecule, and that is why you should add another 4 electrons to xenon, and only by that way we can make it confirm. Okay, so now I'm going to Menti question. Please go to the Menti question once again. I have another 1, 2 in fact, but I will just do 1. Okay, this time I didn't make mistake. And the code is, I paste it here. Okay. Yes, use this code and please try to answer which one do you think the best possible structure for nitrogen dioxide gas. Okay, do it faster. This is the last thing that we're doing today. And tomorrow we'll have class again at 9. Faster, 1 minute. Faster, 30 seconds, less than 30 seconds. We are 19 here, but only 14 votes so far. Where are the others? Faster. 10, 9, 8, 7, 6, 5, 4, another 3. Who are the 3 then? Okay, so time's up. We have 16 votes, not too bad. Now let's see which one is the maximum. The display image preview. Why don't I get the result anymore? Wait, I need to download the result. Oh, B, most student got the B1 and 3 student got A, 0 C, nobody liked C. But let's see what is the correct answer. What is the problem with this A? Most students like B, yeah? So what is the you say you've been tricked. You have been tricked because the B looks so plausible, yeah? Because there are 4. I mean, everyone has 2 oxygen has 8 electrons around it, octet filled up, and yeah, nitrogen also has 4 bonds. So nice. But the problem is, if you do the formal charge, just do the formal charge. Let's see how I have done. Let me find out where did I do it. The formal charge for nitrogen oxide, or nitrogen dioxide, in fact. Okay, anyway, I cannot find it. But let's calculate the formal charge for B, oxygen. For B, oxygen, the left side. So when it is in the question, in the answer, in the question, in the test, you have to denote one oxygen as A, one oxygen as B. If this type, or for there are 3 oxygens, O3. Right? So you have to denote one oxygen A, another one is B, another one is C. Okay? And for all the possible structure, and you have to give us the formal charge for all A, B, and C. All right? So for, let's say, I denote this as A oxygen, this is B oxygen. How do I? Okay, I don't have any other, I cannot write. Okay, so for B, I have the left one. Oh, you cannot see my screen. Okay, I think you can see my screen now. So for B, for the left one, oxygen, the left one, all right, it has the formal charge 6 minus 4. 6 is the valence electron it has, minus 4 that is available now, and minus the bonding electron, that is 4 bonding 2. So it will be 6 minus 4 minus 2 is 0. And for these 2 oxygen, 6 minus 4 minus 2 is 0 as well. So both of the electrons, oxygen has 0, 0 formal charge. Very good, very stable, nice. What about for nitrogen? Is 5 minus 1, because there is 1 electron here, lone pair. 5 minus 1 minus 4. 4 bonds, so 8 electrons by half of 8 is 4. So 5 minus 1 minus 4 is 0. So all of them has 0 charge. So that should be the nicest one. But remember, this is the periodic table and nitrogen is here. Okay, is the 5A. It cannot go beyond 8 electrons. It cannot go beyond 8 electrons. It does not have the capability of going beyond the 8 electrons, because the electronic structure of nitrogen is 1s2, 2s2, and 2p5. It cannot take 2p7. Or it cannot have any d orbital. It does not have any d orbital, so it cannot expand. No matter how much available electrons are there, nitrogen cannot take more than 8 electrons. So since we are telling about, here it is 9 electrons for nitrogen already, because 4 bonds is 8 electrons, and there is one, here is another one. So 9. So this is not correct. It's impossible. Nitrogen cannot have 9 electrons. All right. But for A, we see that this is 0, just like this oxygen formal charge will be 0. This oxygen formal charge is -1, and this nitrogen formal charge will be +1. So this is the best possible solution or structure that they can have without overburdening their size. Otherwise, they will expand and then burst off, right? Nitrogen cannot have expand and burst off. And so A is the final answer, I mean, correct answer. So A is the correct answer for this. Oh, I just had to press S so that I can have the, okay, good. Enter to show the correct result. Do you see the correct result now? Anybody? Okay, so nobody talks. So anyone has any question so far? If no question, then I'll see you tomorrow morning. And thank you for attending the class. If you have any question, of course, you can email me anytime. All right, or you can, yeah, reach me individually. All right, so I'll see you tomorrow morning.